record?
Yeah, it's recording.
Okay, perfect. Okay, so Happy New Year, best wishes, as I said, for 2021. I hope it's gonna be in best condition than 2020. I don't know. I hope you had a good time and some rest during these holidays. I don't know if you had some time to open your electrokinetics lectures and exercises. So I don't know if you already have some question on the past session, or should we start right now with some new concepts? Just let me know if. So as a reminder, last time, so we were trying to find the current in electric circuits using various methods. We start with Kirchhoff laws, then we saw the superposition theorem, and that's it. So today we're going to see two new theorems, Tevna and Norton theorems, and I'm going to put them in parallel to explain you how we can use them and to see that there is some connections between these two theorems. So no questions on the past sessions, no black points or miss. Yeah, if you have any issues with the past sessions, is it okay? Can we start?
Yes, it's okay.
Okay, let's start. So first thing, get my pen back. Here it is, and let's start. So, do you see my screen? Yeah.
Yeah, we do.
Okay, perfect. Yeah, I don't know why I have 3 different screens and one of them is black, and it seems that this is the one that you are recording, but apparently you see my tablet. So let's go. So today we are going to see, as I said, two new theorem. So Tevna theorem and Norton. So from the beginning, we saw other methods to solve our problems, to try to find some parameters in circuits like voltages or currents. At the very end of this electrokinetic part 1, you will realize that in fact Kirchhoff laws won't be, they are useful, but this is not the best way and the more pertinent or straightforward way to go. After you've seen all these theorem, maybe you will get used to apply this theorem instead of going through Kirchhoff. So what about these two theorems? In fact, when you use this theorem is to simplify or to redraw parts of an electrokinetic or whatever electric circuits you have. So let's say that you have something quite complex like this. Make it very complex for the example. A, B. This is some resistors, a voltage generator, current generator. The idea behind these two theorems is to take part of a circuit and simplify it by what we're going to call a Tevna model or Norton model. So let's say here in this example, you want to simplify everything which is in the circle. If you apply Tevna theorem, everything that you have in this green circle is going to be simplified by a Tevna model, which is a voltage generator in series with a resistor. So at the very end, when you are done with a Tevna theorem, you will get something like this. So you would say, okay, in between A and B, I have this resistor R, let's call it R1, and the rest of the circuits was simplified using the theorem by this. And that's it. So, of course, the idea is to simplify greatly your circuits. This is Tevna. And this is what we call the Tevna generator or Tevna model. Norton is exactly the same. So take part of a circuit and use this theorem to simplify it, except that at the very end, you will finish with a model which is a Norton generator, which is a current generator, in parallel with a resistor that we're going to call the Norton resistor. So again, at the end, you will have the resistor R1 and the rest of the circuit is now simplified with this model. Is it okay for the overall concept? Quite simple, and as you can see, it's going to ease your life greatly. So now, how are we going to apply them? I'm going to detail step by step kind of a protocol that you have to apply strictly to not forget any step or sign or something like this. So let's start with Tevna. Okay. So first step, need to, so as I said, when you apply this theorem, it's when you want to simplify parts of a system. The part that you don't want to simplify is called the load, charge en français. So you have to consider what is your load in your system. If I just take this quick circuit, and if I want to apply Norton theorem between A and B, this R1 is called the load. So I'm not considering this resistor when I'm going to apply the theorem. So it means that I'm going to simplify everything except this resistor. So first thing, I'm considering the load and I'm getting it out from the circuit network. So you can redraw your circuit without the load. At the very end, once the simplification through the Tevna theorem is done, don't forget to replug it. So first thing, what is the load? So what I'm considering in the TEVNA model. Once you are done with this first step, then you need in TEVNA model two parameters, which is what is the voltage of the Norton generator, which is a voltage generator, and what is the resistor, which is called the TEVNA resistor, equivalent to what is inside this red cycle here. So first thing, how are you going to get RTH? So first, what is the load? And of course, get the load out of the circuit. So if I go back to my example, then I have something like this. All right. So to get RTH, first thing, so you're now on considering this circuit here. First thing is to turn off all sources. Turn off all sources. So remember to turn off a voltage generator, it's a single wire, and to turn off a current generator, it's an open circuit. And you redraw the full thing. So back to my example. Now I have something like this. All right. From now, to get RTH, I'm looking for the equivalent resistor that I see between A and B. And this is going to be RTH. So here it's quite simple. These two here are in parallel, so you can simplify them. Then you will have this guy. Once it's simplified, let's go quickly through this. So let's say that this is, let's simplify, 2R, 2R, this is R, this is 2R. So these two are in parallel makes R. Then you have the something like this with 2R. These two are in series. So you have 2R in parallel with 2R, which makes R. So RTH in our example is R. Is it okay for everyone, or should I slow down a little bit?
I think it's okay.
Okay. So I got the first parameters of my TEVNA model, which is this RTH. So I have RTH here, the equivalent resistor that I've seen between A and B. Okay, now I go for the next parameters, second one, which is how I found ETH. So to get ETH, first thing is to not forget to turn on or turn back on all sources. So you go back to the initial circuit and you now look for ETH, which is, so I'm back to the first circuit without the load, and I say now I want here the value ETH. You have now to solve your problem by applying Kirchhoff law to get at the very end this ETH value in this circuit. So at the very end, you have both parameters and you are done with your simplification. Turn back on all sources and plot ETH, find it using Kirchhoff law. One thing which is quite important and sometimes a source of mistakes is the direction you have to follow when you are looking for the ETH voltage. So let's say that you are looking for ETH in this direction. Well, if you want, you can look for ETH in the other direction. The only important point is to keep the direction of ETH. Let's say at the very end of this computation, you find an ETH value of, I don't know, let's say 5 volts, but you find it from B to A. It means that once you go back to your final solution, so A, B, this is your Tevna model. ETH is in the same direction that the one you picked, okay? And this is RTH. That's it. Of course, at this stage, if needed, don't forget the load if you need it back, because you are applying Tevna model only on part of a circuit and not on everything here in this case. Sometimes you don't have to consider load because you are considering the whole circuit, but if there is some load, you extract it from the circuit. It's not entering in your model, in your simplification, but at the very end of your exercise, don't forget to plug it back. Is it okay on the concept of this theorem? Is there any questions?
No, it's fine.
Okay. So this is for Tevna, but for Norton is quite the same. So now we move to Norton. Again, a protocol to get two things: the current which is going out from the current generator of Norton, and the Norton resistor. First step, same thing, load. Norton is like Tevna, is just considering simplification of part of a circuit. So if you're considering a load, something you don't want to consider inside your theorem, you extract it from the circuits and you start simplifying the rest of the circuit. So extract it if needed. Je crois pas. Fais le tour. Oui, je suis en cours, c'est pas grave. So load, extracted if needed. So that's the first point. Then the second point is to find Rn. This Norton resistor is found exactly in the same way that Thevenin resistor, which is for Rn, turn off all sources and find the equivalent resistor between the 2 points you consider. So at the very end, the first thing you will consider is that the two resistors are equivalent. So when you're looking for Norton or Thevenin resistor, in fact, you should find the same value. So this is the first point. And then the second point is to find the other parameter, which is the current IN. So again, for IN, turn back on all sources, and we start looking for this current. We are looking for a current that we're going to call ICC. So let me just go back. So the circuit was something like, I don't remember. Something like this, between A and B. So to get IN, turn back on all sources. Then you put a wire, or you connect, or maybe it's better connect. So you connect a wire between A and B. So a wire between A and B, and now I'm gonna go look for the current flowing through this wire. I'm gonna call this current ICC. Then you are gonna apply Kirchhoff law to go back and find the value of ICC. At the very end of your computation, you will find that the value of ICC equals to the value of IN. The unique single difference is that the direction of ICC is opposite than the final direction of IN, which means that if you're looking for an ICC which go from A to B, once you solve your computation, gain the value of ICC and so the value of IN, then you go back to your final model. So you are in between A and B, you put back the load, R1, and then when you're going to draw your equivalent Norton model, then you have Rn here, but the In here go in the opposite direction than ICC. You see, ICC go down, and I go up with IN. This is the only difference that you have to pay attention, but the value of ICC equals to the value of IN. And that's it. So two ways of simplifying a certain part of a circuit, and then have something which is like a single mesh circuit. One important thing here, just because it might be obvious for some of you, but here just let me add this. When you look for ITH between A and B, here you see that A and B are not connected, which means that the currents between A and B, so the current flowing through our load previously, equals to 0. Okay, this is quite important. So back here, nothing to add here. So now, another important point in between, so as you have seen, these two theorems are kind of linked together. First, the way of finding their corresponding resistors is the same. And after, for one, you're looking for voltage, and for the other one, you're looking for current, but this is always in between the same 2 points, A and B. So at the very end, you can go from one model to another quite directly. So let me grab another color. This is a Tevna model. And you can, from this model, go directly to a Norton model, which is like this. Other option, you are in front of a Norton kind of model. You can move from one model to another model straightly and change it. So this is Rn equals to RTH again, and here the voltage delivered equals to this. And this is very important to understand how to go from one model to another one. How to, you can apply this directly in an exam, in an exercise. And this is very simple to demonstrate. So how can you demonstrate this? In fact, for the first example, you start from this circuits, which is a Tevna model, and you apply Norton theorem on this. Okay, so here, A and B, I'm not considering any load, and I want to apply Norton model on this. First thing, so no loads, I'm turning off ETH, which is now a single wire, and looking for the equivalent resistor between A and B, which is RTH. So again, I found RTH equals to Rn. Then I turn back on ETH, link both A and B, and now look for the current ICC. So if you go like this, you will find that ETH because of the mesh law equals to RTH time ICC. And so you finally find that ICC, which is the value of IN, equals to ETH over RTH. Be careful, as I said previously, here ICC is going down, but here IN is going up. So this is when you apply Norton model, but if you don't want to apply it or you're applying this directly in your mind, going from this model to this one, then you have to keep the direction of the sources. Here you see that ETH is going up. So here, when you simplify it, here your Norton model is also going up. Okay, so you keep the direction of your voltages. So this what the first case is. Second case is here, how to demonstrate this. Again, quite simply, you apply Norton model on this. So here you have A and B. So no load. You turn off first the current generator. It's open between A and B, and you see that there is only Rn in between A and B. A and B, sorry. So you find again that Rn equals to RTH. And then, of course, you look for ETH in this direction. Okay, so you are back. Let me redraw this maybe clearly here. You're looking for ETH here between A and B. And it's quite simple. As I said, between A and B, there is no current flowing through it, which means that the current here equals to 0. IN is flowing like this. So IN is flowing like this. So here you can consider a voltage between this point and this point, which is the voltage in between Rn, which is directly ETH, because this point is this point is this point, same potential. This point is this point is this point, same potential. So at the very end, ETH equals to this voltage is here, which is already Rn time IN. Okay? And this switch between this quick switch, because now I demonstrate here everything, but as I said, you are allowed to apply this directly in an exercise. And this is what we will see right after, and this is called the simplification theorem, or the equivalence theorem, which is only using this quick comparison, this quick exchange between Norton and Thevenin model to simplify your circuit. And that's it. So it's a lot of information for this for today, but you're going to use this a lot, especially this equivalent simplification theorem after. Do you have any questions from now on Norton or Thevenin model?
Yes, I have a question.
Yeah.
So do we always use the generator? I forgot the name. Oh no, it doesn't matter. When we go to from Norton model to the other one,
Yep.
do we always use the generator convention?
Well, what do you mean? When I put IN here?
Yes, because if we use the receptor convention, it goes on the other side. So if we do everything with the receptor convention, would it also work, or do we have to use
Yeah,
the...
no, it will also work.
Okay, thank
But
you.
again, don't complex your mind, don't confuse yourself by trying to get a complex convention which is going to add you a negative sign here and there. But again, you will end up with the same result.
Thank you.
Okay. Other questions?
No.
All right. So now, since everything seems to be fine, your turn to work, which is back to our circuits. So let's move here to the circuits we consider, which is this one. So we are back. I don't remember the number of the exercises, but so yeah, we are still in exercise 6. So this is our circuit. And 0, R1, 2, R1, 2, R1, R, and we are still looking for this current here. So now you're going to practice Devna and Norton theorem. So you're going to pick A and B here. Start with Devna model. So considering R here being the load, which means that you are gonna apply Devna model on all of this. Why are you not including R in the model? Is because of the current I you're looking for. If you put R in the theorem, then you won't be able to go back to what you're looking for, which is the current I flowing through the resistor R. Okay, so go for a Tevna model. Try to follow step by step the protocol I show you, and you already know the result, the final result you should find. Once you're done with Devna model, go for Norton model. And I'm just gonna give you the intermediate result of ETH and IN here. Okay, so I leave you work on that, and just I'm gonna write you the different intermediate result here. So I was looking for ETH from A to B, and in that case, I found that ETH equals to minus R1 I0 minus. But of course, you can find ETH from B to A, except that you will have the opposite result. But what is important at the very end is to find back the currents I, and this current is, direction of this current is already fixed, and you should find back the result of the current that we already found. Which is this. If you have any trouble, questions, please let me know. If you are stuck,
Yes, excuse me.
Yeah.
I never understood the concept then, but because I thought RTH, I thought the load was the what we were looking, well, not what we were looking for, but I thought it was where the resistance where I was what we were looking for. But is it the resistor where the generator is? Is that
So,
right? R1?
well, when you apply Tevna model or Norton model, here in this case, the idea is to simplify everything which is inside here, the green circle. So at the very end, you will, if you apply, so Norton model
Because if
between,
we apply the Kirchhoff laws, we find that it's 2R1 with the. That's just my question.
your question is why I found 2R1 here?
No, it's just I thought we were just taking R. I thought the.
So the idea here to get RTH or RN is to get out the load R between A and B. So you redraw your circuits like this. It's applying exactly the protocol I gave you. So I get out here and turn off sources, and you end up with this. Okay.
Mm-hmm.
So now the question is, what is the equivalent resistor that you see between A and B? This equivalent resistor is going to be the RTH or the RN we are looking at.
Okay, yeah, that's okay. Thank you. That answers.
Okay, perfect. So the main mistakes you can do applying this theorem is to forget to turn off or to turn on back or turn back on the sources. The sign problem, forget to keep the direction of ETH or to change the direction in between ICC and IN when you are redrawing your model. Also, something I used to see in past exams, some common mistakes is once you get RTH, ETH, or RN and IN, then you think you're done. So you stop the exam and say, okay, yeah, I found the result, but the result is not giving me the model of Norton or giving me the model of Tezner. In this exercise is to find the currents I flowing through R. So keep in mind what we ask you to do and don't stop once you get your final result for the model. So everybody is capable of finding the equivalent resistor between A and B and find the 2R1 result.
Yes, but I have some troubles with the second part.
Oh, for finding ETH?
Yes, and this single cable between the two
Okay,
meshes
so
confuses me.
okay, so now so for the equivalent resistor between A and B, is everyone okay with that, or should I spend some time here again or not?
No, it's fine.
Okay. For everyone, can I erase this or
Yes.
okay? So first step, you find the RTH. Now you're looking for ETH. So turn everything back on.
Okay, sorry, I found out how to do it. Thank you.
Ah, okay. Just redraw and B. So I found ETH like this. Put it back in my circuit. To R1, to R1, R1, I0. So this is the circuit you face. The question is, what is ETH here? So you see that now the only thing you have to apply is Kirchhoff law. Again, same protocol as we used to apply is to so here there is no current flowing between A and B. Here the current is 0, which means that there is one current flowing through here, which is I0. And there is another current flowing through here, which is I1. Well, you can say that there is another current here, but this is not quite important because when you arrive here, there is only one I1 flowing through this. So even if you say that this is I2, I2 equals to 0 anyway. Because this point here is the same than this point here. C and D is the same point. Then you go, once you have your currents, you go for your voltages in the receptor convention, and then you face these fully labeled circuits. You already applied node law, so you have to apply mesh law. Remember that I have here a current voltage, so it's not very smart to apply a mesh law in a mesh featuring a current generator because you don't know what is the voltage in between the terminals of your current generator. So here you have 3 meshes that you can use. Let me grab another color. You can use these meshes. You can use these meshes. You can, yeah.
Why is I2 equal to 0?
Well, in fact, as I said, that the point C here equals to the point D here. Okay. So in fact, in this wire, it's like it's not existing really. So, but if it confuses you, let's keep this with a current called I2. But you will realize that you won't use I2 in any of the equations you're gonna play with. So in fact, you don't need it.
Okay, so it's like because there is nothing that we can say it is equal to 0.
Well, it's the other important thing when you face such kind of circuits, and once you're going to be trained a little bit with the circuit, you will realize that the currents here between A and B is the same current than between D and C. So since in between A and B the current is 0, then in between C and D it's 0. But you will see this later once you will do a lot of circuits. But from now, yeah, don't think too much about it. Just put another current, let's call it I2, and keep processing your circuits as you used to do. And then you realize that you don't need I2, and that's it.
Okay, thank you.
And we can use a mesh even with
Yeah,
connected.
the large mesh, you can use this also. A mesh is just shallow, so it's just a sum of voltages, and you can consider voltages between 2 points that are not linked by a wire.
Yes. Okay.
Okay.
Thank you.
The mesh law is law is like a sum of vectors. So whatever you can consider difference of potential between 2 points that are not linked by a wire, it's a difference of potential. But if they are not linked by a wire, it means that there is no current flowing between A and B. But it doesn't mean that there is no voltages. There is a voltages as long as there is a difference of potential between 2 points. But this is an important concept to really understand. So when you are considering a square like this with various voltages, you can apply a mesh law here because you're only considering vectors. But you cannot say that A, B, C here is really an electric circuit because there is no current flowing through these different points. So in this particular case, in fact, applying Norton or Tevna model is not really a simplification regarding the calculation computation you have to do, because here you still have to apply multiple times some mesh laws and have a system of equations. So can we say that this is simplifying your life here, applying Tevna or Norton model? Not really, but here you are practicing it. Then if you're done with Tevna and Norton model, the idea is to try to apply the simplification theorem, which means that we are looking for either Tevna or Norton model, and we're going to move from one model to another one to try to simplify step by step and little by little these circuits down to a single mesh one.
Sorry.
Yep.
I still don't know how to find ETH.
ETH.
Well,
So back to our circuits here, okay? So you have three different meshes, okay? What are the unknowns here? The first unknowns is the current I1, you don't know it, and the other unknowns is ETH, correct? So you need only two equations to solve this system with these two unknowns. Does it make sense?
yes.
Okay, so now you just have to write at least two equations from mesh law, and you have three different options. So first one is applying, so let me take another color here, brown. So mesh one here, I have ETH plus R1 I0. So I'm going in this direction. So ETH plus R1 plus 2 R1 I1 equals to 0. Do you agree with this first equation?
Yeah.
Okay, so now you need another one. You can go in these second meshes here. So I'm gonna go this way. So I have E minus 2R1 I1 minus 2R1 I1 equals to 0. Still okay with this equation too?
Yes.
Okay, so you realize that from equation number 2, you get directly the value of I1, which is E over 4R1, that you re-inject in this equation to get the value of ETH. Is it clear?
Yes, now it is. Thank you.
Perfect. And so you end up with the result of ETH we're looking for. Then it's not done because, as I said, don't forget to put back the load. So now you have your load R between A and B. You plot your model, Tevna model between A and B. ETH is, in my case, like this because I was looking for ETH between A and B, so same direction, or TH like this, and I'm looking for the current flowing through A and B, which is the current here. So here you are in front of a single mesh circuit. You apply the the mesh law, and you're done. And you should be able to find back this result.
Okay, thank you.
Perfect. So for Norton, you're looking for the same resistor, and then you have to redraw your circuits linked A and B with ICC. So
It's 9:07.
yeah, perfect. Okay, we can stop here, no problem. So for next time, just have a look on your lecture document on page 24 and 28 and 28. Sorry, because this is just a reminder of the two theorem we've seen today, Norton and Tevna theorem. So you should be able to understand this now quite easily with this other explanation. If you have problems, please let me know. We will meet this Friday. So if you have questions by the meantime, feel free to drop me an email. If not, keep practicing on these circuits to find the two models using these theorems. And this Friday, we will apply the simplification equivalence theorem, and also we will see the very last theorem, which is Millman theorem. All right?
Excuse me.
Yeah.
Do you have any informations about how it's gonna work for us? Because we talked about some other teachers, they said that we were allowed for 10 of us only to go back to class. So
This is something which is actually under discussion, and it's really dependent on the matter, the subject, and the teacher. My opinion on that is I don't want to, well, I prefer take some of you which are really having issues at the very end of the class, having an extra tutorial session, instead of taking 10 of you next time. I don't know how to pick the 10 of you. So yeah, I don't want to make this judgment, and I don't really agree with this 10 people group opportunity. So in my case, I won't ask 10 of you to come physically here, especially because it's only for the next 2 weeks. I don't get really the point of that. But the other option is adding maybe an extra session of tutorat if needed. This is how I see the end of this class. But maybe, well, maybe other teachers will allow you to and will ask you, 10 of you to come. I don't know. but that won't be my case.
Okay, that was my question.
Okay. Okay. Yeah.
You just put the previous slide on.
Sorry. Yeah. Here we go.